I am Débora Sanches, electrical engineer and researcher at Search Foundation, and I will present this work, Dynamic Pricing for Electric Vehicle Recharge at some fast charging station. Can I start? Okay. The replacement of combustion engine vehicles by electric vehicles brings great advantages, such as lower maintenance cost, noise reduction, and reduction in the emission of pollutants, and these factors making it a more economical and efficient alternative. But, however, with this, the fleet operator has a new challenge because the difference between the charging time of electrical vehicles and in some fast charging station can bring some new situations like unnecessary queues, distribution network overload at peak hourly, vehicles unavailable because they are charging during off hours. And the specific case of this study includes an energy distribution company that is electrifying its fleet, the electrical vehicle fleet, the charging station, some include photovoltaic generation and others not, and the distribution network. So the purpose of this study is to solve this challenge, ensuring the use of electric vehicle fleet and the charging station at the best times, both for the company, for the users, and for the distribution network. In this context, this paper presents a charging strategy focusing on some fast charging stations. Is an original model that will guide the user behavior through dynamic pricing, promoting the charging of the fleet outside the office hours. In addition to encouraging that when charging station has photovoltaic generation, the charging is made during the generation hours, ensuring simultaneity between local generation and local consumption. In Brazil, it is important to say that there is no regulation for the payment of electric vehicle recharge. This is expected to be defined in the coming years, and this work is a part of a research and development project and is even contributing to the definitions of regulations of recharge payment with the regulatory agency. So let's see the proposed dynamic pricing model. The price must consist of some factors. The first one is the current tariff. Thus, for peak hours, the price is higher than during off-peak hours. After we have the operation and maintenance cost of the charging station, the cost of photovoltaic generation, and the hourly fee when it is in off hours. I will explain in the next slide how calculate all these things. Then, with the dynamic factor, the price can modulate up or down according to the current demand in the charging stations. If any connector of the station is free, the price decreases. And if the charging station is full, the price increases. And the last one, the PV incentive, with this incentive, the price can be reduced according to the photovoltaic generation at the station. At times when there is more photovoltaic generation than the demand at the station, the price is reduced. And when the has a little bit photovoltaic generation, the price doesn't change. This is to encourage the user to charging and have simultaneity between generation and local consumption. So the fee hourly exists in this model specifically so that vehicles are available during off hours, enabling the better possible use of the fleet. And is this the equation of this factor? The dynamic factor makes the charging station price dynamic based on the relative occupancy rate, and the PV incentive alpha makes the price go down depending on the PV generation conditions in the panels connected to the charging station. So we have the dynamic price equation, and this price contains the current tariff, dynamic factor, PV incentive, operation maintenance cost, cost of PV, and generation and hourly fee. And the discretization is 30 minutes, and we have the algorithm described in steps. So for each station J in period T, search current data time, the current time and input data, this data, calculate the adjustment hourly fee, calculate dynamic factor, calculate incentive coefficient, that is the PV incentive, and calculate the dynamic price for station J in period T. Now let's see the resultant analysis. The simulation that we did after the implementation is this that I will present now. For the simulations, we choose 3 hypothetical scenarios based on the office hours in the company, and we have charging station with PV generation and without PV generation. The first input is the photovoltaic generation curve, and was simulated for summer in 4.8 kilowatt peak carport in northeastern Brazil using the software PV System. And we have these fixed inputs. So we have the operation maintenance cost, the cost of PV generation, the initial and the end of the office hours, T initial and T end, the tariff peak and the tariff off peak. The values are based on Brazilian money, the real, and on the date of the submission of this paper was a little more than $5. Let's see the results. First, for workday scenarios, we have this hypothetical schedule load demand scenarios. So the current demand is an input, and below you can see the results as a dynamic price. As you can see, when demand for charging is very high, the price is also high. And when demand is low, the price is low. Here at 9 a.m., we can see the difference between a station that has PV generation and the one that doesn't have PV generation. Where there is PV generation, in purple, the price is much lower than where there is no PV generation, in pink. So we can see that in the middle of the day, although there is PV generation, as demand is very high, the price also goes up because it is not reasonable to reduce the price when the station is already full. Also, we can see that the peak hours from 6 p.m., the price goes up and is only reduced again when peak hours end at 10 p.m. Now let's see the results for Saturday scenarios. Here we have these hypothetical schedule load demand scenarios, this input, and we can see the result, dynamic price below. And as we can see, when demand for charging is very high, the price is also high. And when demand is very low, the price is low. Here at 9 a.m., you can see the difference between stations that has PV generation and one that doesn't have PV generation. And where there is PV generation, in purple, the price is much lower than when there is no PV generation, in pink. And we can see again, in the middle of the day, although there is PV generation, as demand is very high, the price also goes up because, again, it is not reasonable to reduce the price when the station is already full. On Saturdays, has some difference because on Saturdays there is no peak hour in Brazil. So the distribution energy tariff remains the same all the day. Now let's see the results for Sundays and holidays. And again, we have these hypothetical schedule low demand scenarios. And as you can see, when demand for charging is very high, just in this moment, the price is very high. Here at 6 a.m., we can see the difference between a station that has PV generation and one that doesn't have PV generation. And again, at this time, we can see the difference that demand provokes in the dynamic price. We can see that in the middle of the day, although there is PV generation, demand is very high, and so price goes up. And because this is not reasonable to reduce price when the station is already full. On Sundays and holidays, like Saturdays, also there is no peak hour, so the distribution energy tariff remains the same all the day as the last example. So concluding, the model managed to modulate the price of electric vehicles recharges in semi-fast station through difference in the part of the day, demand of the station, and PV generation. This model encouraged the charging of vehicles at opportune times, carrying out the temporal displacement with the hourly adjustment fee, and the applied dimension factor performs the special displacement, increasing prices in stations that are very overloading in relation to their capacity. The PV incentive factor contributes to take advantage of PV potential of the station, reducing the price in times of greater solar incidence. So there is simultaneity between photovoltaic generation and the recharge of electric vehicles. This model is new in Brazil and is being built for the application within a research and development project in the basic research phase. For future work, you'd be interested to implement the model in pilot of electric fleets to validate the results in relation to the modulation of the behavior of users with the price variation. Another suggestion for future works is to simulate the dynamic pricing for some types of electric vehicles with different batteries and compare the results. Thank you for your attention, and let me know if you have some questions.
Well, thank you very much, Débora. We have some minutes for questions. Si hay preguntas, las pueden hacer en español por el chat. Please ask your question by chat. And if si son en español, yo puedo traducirlas a Débora. We can wait some seconds or a minute for questions. It was a very interesting explanation. Up to now, we have no questions, but we can wait because people need some time to type the questions. I saw other presentations where there was no time to type, so some people wanted to perform some questions, to ask some questions, and couldn't. But
yeah.
Well, if there is no question, perhaps at the end of all sessions, of all presenters, we can if we have some minutes for question, we can complain. We can have some question for your presentation. Well, thank you very much, Débora, for your presentation, and very nice presentation.
Thank you.